Hi everyone. So this video is about a very important design factor when using mini batch methods or stochastic mini batch methods, which is basically choosing the mini batch size, or just as an to be concise, choosing the batch size. As we said in the last video, the words mini batch and batch are used interchangeably. So there are three aspects that you can think of for choosing the batch size, and actually the three aspects are interrelated, and many of the choices are related to more than one aspect, and that's why the comments here in the notes are in no specific order according to these three aspects. The three aspects are statistical efficiency, right? So basically that determines the quality of the gradient estimate that you obtain when choosing that mini batch, when computing the gradient estimate based on that batch. The second aspect is the optimization strategy, right? So this is the path or the trajectory that you take based on the gradient estimate computation that you take in order to minimize the cost, right? And the third aspect is computational. Right? So what's the computational hardware that's being used, and what's the architecture of that computational hardware? For example, the GPU or the CPU architecture that's being used. And also computational, the concern here is computational cost, right? And both in terms of hardware, like the hardware used and the time needed, the computation time. So statistical, optimization, and computation. Now, the first comment in the notes here is, for example, purely on the statistical aspect. And it says that larger batches typically provide more accurate gradient estimates, right? So let me add here, typically. Why typically? Because it depends on the training set. This comment is based on an assumption that the training set doesn't have redundancies, right? But as we mentioned last time, smaller batches can even be good even for the statistical efficiency aspect, or for obtaining a more accurate gradient estimate or an unbiased gradient estimate, if the larger batch would have redundancy. So if the training set has a lot of redundancy, there is less likelihood of having redundancies or repetitions in a smaller batch selected from that training set, right? So from the statistical efficiency perspective, if the training set is rich enough or diverse enough, then you want to go for larger batches. Okay, now let's talk a little bit about the computational aspect. As you would expect, larger batches would basically take more time to compute the gradient, and hence to do one parameter update. But at the same time, because in many cases you can compute the gradient corresponding to different examples in the same batch in parallel, especially if you are using a GPU or a hardware that facilitates faster computation in parallel, then, or a multi-core architecture, a multi-core CPU. So typically these multi-core architectures, there is a way to parallelize the computation of the gradient with respect to different examples in the same batch, and hence small batches may underutilize the resources. Now, actually, because of the specific way that some of these architectures are built, the batch size need to be aligned with the architecture underlying the the processing unit. So, for the case of GPUs, it's common to use powers of 2, typically 32 to 256 with the current technology, and now you can go higher, especially if you have multiple cores, and you can aggregate these cores and parallelize across the different cores, right? And then so the same batch can have different examples within the same batch, having the gradient estimate computation happening on different cores or on different GPUs. So in these architectures, you can go above 256 with the current technology, but it used to be the case that typically you have a batch size from 32 to 56 to align with the architecture underlying the processing unit. Now, the available memory can also be a limiting factor. Like having very large batches, you can go easily out of memory, that there is no memory to basically, because the computation happens for the whole batch, whether forward or backward propagation, right? So you vectorize or put the hidden vector, the hidden units as well as the input units of all the examples in the same batch together, right? So the computation, you can go out of memory if the batch size is very large. Now, back to the statistical and optimization aspect, small batches can offer a regularizing effect, right? Why? Because my gradient estimate is not very sensitive to the training set, because I took only a small subset of the training set. So it's not easy to overfit if the batch size is small, right? Because I don't know, I cannot really custom tailor the solution to the exact patterns in the training examples or to all the details in the training examples, because many of them are missing in the batch that I use to compute my gradient. So in that sense, small batches can offer a regularizing effect. But at the same time, when I have a smaller batch, I have to use a small learning rate. Why? Because I don't want to take a big step, right? And that's what the learning rate governs. I don't want to take a big step based on only a few training examples or a small set of training examples, right? I want to take a big step only when I have confidence of doing so, right? So imagine the trajectory when I'm navigating the parameter space, the cost function on the parameter space, right? So I don't want to take a big step in that trajectory unless I have a large number of training examples used for the computation of the gradient direction behind this step, right? Also, the choice of the optimization strategy can be crucial to the choice of the right batch size. For example, if I am using a second order method, then my computation relies on computing the estimate of H inverse G, as we will see later in this section. That can require a very large batch size if the Hessian has a poor condition number, and the condition number for the Hessian matrix means that it's very sensitive to errors in estimating the gradient, right? So a matrix that has a poor condition number is much more prone to errors when multiplied by other vectors or matrices, right? So when I invert the Hessian and then multiply it by G, I am more sensitive to errors in G, right, in my estimate of the gradient if H has a poor condition number. So if I am using a second order method, right, so a second order method is basically computing an estimate of H inverse G, right? And it's called second order because it relies on the second order derivative information. If H has a poor condition number, then I'm very sensitive to errors in G, and hence I don't want to have these errors, right? And hence I need a larger batch, right? So second order methods will typically require a larger batch size and hence a larger memory, right? So more computational resources. Now, let's go back to the statistical aspect. Ideally, we want the mini batches to be selected independently to obtain an unbiased estimate of the gradient, right? Now, every time, if I have a very large data set and I want to select many batches independently to draw from that very large data set every time I have a training iteration, that could be very costly computationally. So what's typically done, and there is empirical evidence that it works very well, that if we have a very large data set, we shuffle that very large data set once, and then we store it in a shuffled fashion, we store the shuffled version, and then we select the many batches in a deterministic order from the shuffled training set, right? That can also be useful for benchmarking if I want to compare between different models, because the randomization in selecting the mini batch could create a difference between selecting the different models, right? On the other hand, this could be bad for bagging, because for bagging, we want bagging that we discussed in the last section, the bootstrap aggregating, we want diversity between the different models, right? So if you have, so selecting the many batches independently could be advantageous in bagging, but if you are comparing between how different models perform and you want to select the best model, this could be advantageous to fix a shuffled order and then draw the many batches in a deterministic way. So most implementations use this shuffled approach and then pass through the data multiple times. And every one time, one complete pass through the training data is usually called an epoch, right? And having multiple epochs is typically useful, even though the further passes on the training set usually introduce a bias in the training estimate. But why does it work? Because usually deep learning works with very large data sets. And in this case, the concern is typically underfitting and computational efficiency rather than overfitting, right? So that's why when you go multiple times, you are actually reducing underfitting. You can fit better to the training data. And because it's the predominant concern or the main concern rather than overfitting, but at the same time, regularization can be very important, right? So this sounds a little paradoxical, but as we discuss more, it can be clearer when underfitting is the problem and increasing the number of epochs needs to be done, and when overfitting becomes an issue. And typically, that's why early stopping is typically used, because in the early iterations, the data set is very large. So even though I'm introducing a bias to the gradient, what matters now is that I'm reducing underfitting. So I'm fitting better to the training data. But then as you navigate the U validation curve, it becomes more important to avoid overfitting. But at least early, like one pass is rarely, or one epoch is rarely enough for training deep learning models. Thank you.